Hi guys, we are super excited to be presenting on how we've been projecting UNC's electricity demand over the last 10 years over the next 10 years this semester. So to go over our project, we'll be doing a project overview, diving a little bit into our methodology, then the results that occurred from this, and then a recommendation based on our results. Our key objectives here today are to show you how we've evaluated the projected growth in electricity over the next 10 years at UNC, distinguishing trends by end use, and considering a range of possible scenarios. We also want to propose several policy, technical, and educational measures at UNC that can be taken to mitigate the increase of electricity demand with an emphasis on these different end use cases. And then finally, we've compiled all our findings into a comprehensive technical report that clearly outlines the research foundations, assumptions, analytical approach, results, and recommendations.
Alrighty, so here's just a reminder of kind of the past 5 to 6 years, and so that we can get a better idea of that and how that played into our model moving forward. The few sectors that we decided were the most important with our model are going to be academic affairs, so that's going to be any classroom buildings, whether it's graduate or undergraduate level, as well as chillers made up a huge proportion, and health affairs, which all hospital electricity was not included for our model. However, health affairs still makes up a large portion just due to the high electricity consumption of labs on campus.
Okay, so to begin our research, we first started by conducting an in-depth literature review, and we split into 3 teams to do this. One team was focused on looking at models that other universities are currently using to project their own electricity demands, and 2 campuses really stood out to us. The first being the University of Missouri, which they used their unique environmental data that they had and contextual data to create a high-resolution model for their electricity consumption, while comparatively UT Austin had a digital twin where they're able to look at past, present, and future electricity demand of individual buildings on campus. The second team went in depth to analyze UNC's campus plans to find potential variables that would be impacting our electricity consumption in the future. Our main takeaway from this was that student enrollment is definitely going to increase over the next decade, specifically by 5,000, while they'll be adding additional new beds and renovating buildings, as well as additional housing to house students. While this is true and will cause electricity demand to increase potentially, at the same time, we've seen a trend over the past decade or so that climate initiatives have caused UNC to take initiatives to increase energy efficiency on campus. So we've seen about a 23% decrease of electricity use per square foot of buildings on campus from 2007 to 2021. So we can expect the same trend in the future. And finally, our last team looked at existing models for electricity consumption, not specifically pertaining to universities, but just in general. And our main takeaway from this was that most electricity demand modeling is focused on a smaller time scale, projecting daily or hourly electricity consumption, while we were just trying to model over a 10-year time period for each year. So this was a slight barrier because we had to tweak the models that we reviewed to better suit our time span. And some of the variables that we found common in different models were time series data, demographic, and weather conditions. By combining all that we researched together, we were able to come up with different inputs to put into our model that intersected between whether it just be used for UNC or campus models or electricity demand models in general. And so our 3 main inputs that we had historical data for were building characteristics, UNC student enrollment, and UNC monthly electricity. So we were able to input this into a machine learning model because we had it for previous years in the past. Comparatively, we predict that EV charging points in data centers could have potentially caused changes in UNC's electricity demand, but we didn't have historical data for this. So we had to make assumptions and created a linear regression model to project these. And finally, we realized that climate could potentially have a big impact on our demand. So we gathered data for monthly average temperature and yearly cooling degrees so that we were able to see how this affects our demand.
So getting into the model itself, as Kenna was saying, we combined a bunch of different parameters. So to predict building demand, we broke that up into various components such as health affairs, academic affairs, chiller plants. And we used our own independent statistical predictions for temperature and student population to get future values for that to input into our building demand model. And then there were a number of things that we didn't have enough data for to include in the model itself, specifically data centers, EV chargers, and data on building renovations, construction, and demolition. So we modeled these separately in Excel. We created our business as usual, high impact and low impact scenarios based on those predictions. And then we simply aggregated that with the building demand model to get our final projections for the next decade. So this is our overall prediction. We'll get into more of the details of this, but I want to highlight at the beginning of class, we said we expected demand to increase. But as Kenna found earlier, and we discussed in the last presentation, the use of AI here does not directly impact UNC's electricity consumption. So what we predict now is sort of this linear downward trend. This makes sense. In the past 10 years, despite increases in population and square footage of UNC, the demand has gone down. So we essentially predict this trend to continue. And I wanted to highlight a couple of specific components, building categories. So the academic affairs shows this sinusoidal downward trend. The housing and cogen categories show a very similar graph. So I've just shown one. We use linear regression for this. It achieved a good 6.4 mean average percent error. That's very strong. And the main thing to highlight here is the overwhelming predictor. The most influential predictor was year. So what that's telling us essentially is that, so year picked up this downward trend. What that's saying is we didn't include some variable, which we assume is building efficiency. That was the real reason for that downward trend. So we're not modeling that explicitly, and the year is kind of picking that up implicitly. So again, the overwhelming assumption here is that the variables that we don't account for, like building efficiency, are going to continue on the same trend. So then switching down here to the health affairs model, we use nonlinear regression. It also got a good mean average percent error score. We, for this one, used inverse year, which is a reciprocal decay feature. And the reason we used that was because using year, it predicted a quadratic trend. And we didn't think that was accurate over the next decade that we would see an enormous increase. So we chose this, the performance was better, and we thought it was more realistic. And this makes the same assumption that chillers and the other category looked like this. So basically, we had 3 categories with a linear downward trend, 3 that were pretty flat, and that led to the overall model being a downward trend. So I wanted to highlight one more thing. Recalling from the past presentation, we had this sort of just flat prediction for everything. The reason for that partially was the lag features. When we would predict, we would use like previous demand to predict future demand. So we got rid of that, but also the machine learning models, random forest and KNN and others, they train on a specific set of data. And if you give them values outside of that range, basically it won't work. So we gave it 2014 to 2025 for year. So when we then give it year 2030, it basically doesn't know what to do with that. So in the literature, we see these models being used for predictions, but first of all, that's over short term. So having that year effect isn't as important. And also they have stronger correlations with other variables that aren't years, like GDP, population, etc. So for that reason, we had to switch to linear and polynomial regression.
Alrighty, so kind of putting it all together, this is how we modeled the 3 scenarios that we talked about earlier. For the 3 scenarios, as we mentioned, those variables were data centers, EV, and building renovations. So as you can tell by our figure, there is a very minimal impact for each of these 3 scenarios. That red line in the middle is our business as usual, which is just building off of the regression model. And then so the yellow is high impact. It's seemed like when we were doing these calculations in Excel, the numbers were pretty big. For example, by maxing out the data center, so all 3 data centers on campus, assuming 100% total capacity usage, adds around 3.6 million kilowatt hours per year. However, when you put it on the big graph, it doesn't really have any huge impact. So these are kind of those 3 variables broken up. We talked a lot about EVs our last presentation, but the building renovation graph in particular, I wanted to spend a little bit of time on just because we had very limited data when figuring out which buildings had been renovated at UNC. We didn't have like a comprehensive list of everything that would impact energy efficiency. We were mainly just pulling from UNC Plan Room and making our own kind of spreadsheet from there. So we ran some calculations over how those past efficiency projects have changed electricity consumption. And then we kind of used those assumptions along with the campus master plan to kind of predict what we expect in the future. That being said, the campus master plan is from 2019. So that is another big limitation we were faced with. And even knowing these factors, like we know population is going to increase by 5,000 students, or it comes to about 15%. We don't have exact numbers on how many dorms, how many new classrooms UNC is planning to build. So definitely that was one of our main limitations, is that building renovations variable. But yeah, just by keeping better data collection in terms of both current and past like efficiency projects, we think the model would definitely be improved upon. And then to kind of round out our model, I know we touched on this last presentation, but once again, these are our survey results. So the most important things that we found important, most students have a kind of average level concern for environmental impact. So it's about a 5.5 out of 10. So they're definitely aware, but they're not necessarily changing their behavior. And when they are changing their behavior, that's mostly coming in with kind of those easy fixes. So they're turning off lights. They're not necessarily unplugging appliances or anything a bit harder or out of their way. They're not making those behavior changes. So just something to keep in mind.
Okay, so clearly this is a limited model, but there are still conclusions we can draw. The main limitation was a lack of data on particularly building efficiency. So the more that can be collected on renovations, lighting, HVAC upgrades, the better. And if there's enough of that, it could go into the model itself. And then we could drop year as that implicit predictor. In that same vein, we didn't find any variable that had a strong negative correlation, so a strong downward trend with the demand. And clearly there's a downward trend in the demand, so we should be finding something like that. And the conclusion we can draw from that is that we're missing that variable, which we assume is building efficiency. Another thing to note, when we change temperature and population in the future, like our future values, it doesn't affect the model much. So this could indicate that those aren't as important as maybe we initially thought. It could imply that something like building efficiency is more important. And that's sort of what our model predicts, is that even if there are unforeseen changes in temperature or population, there will still be a downward trend in demand so long as efficiency continues to improve. But it also meant this sensitivity issue that we couldn't model the different scenarios, the high impact, low impact scenarios with the model, because it basically didn't change. And then finally, we weren't able to use the more powerful machine learning approaches because of their failure to extrapolate over a decade.
In conclusion, our 3 recommendations to help UNC continue this downward trend of electricity demand is 1, definitely prioritize LEED certification. Improving building efficiency is the #1 tool UNC has in driving demand further down in all major construction and renovation projects going further into the future. #2 is individual energy efficiency upgrades like within CO2 sensors, HVAC systems, LED lighting. And then finally, improving communication on a general population basis of distributing appliance guides and improving information amongst the student body in general of efficient use of high draw appliances, and integrating this early within first-year curriculums like first-year orientation, and continuing this throughout the year by maintaining visibility using programs like Campus Sustainability Month. Thank you so much, and we're happy to take any questions.